I am a fifth-year grad student at CUNY Museum of Natural History in New York. I'm entering my sixth and final year, so I'll do the shameless, like, I'm on the job market plug. But we're really happy to have you here. We have a really exciting list of speakers coming up. I'm going to hand it over to Austin to we're going to just give our little motivation for this splinter before we get started.
Okay, awesome. Hey, everybody. My name is Austin Rothermich. I am a fourth-year graduate student, so not on the job market this year, but keep the name in your mind. And yeah, so we just wanted to give a little bit of an intro to what the buddy system is and why we should all care about benchmark systems. So to start off, let me make sure that this works. Cool. So just most people in this room, I'm sure, are fairly familiar with brown dwarves, but just in case you aren't, because we are hoping that we get a lot of star people in this as well. The brown dwarves we typically associate with the late M spectral types down through L, T, and Y dwarves. These are things that form as a byproduct of star formation, but they don't have that stable energy generating mechanism like stars do. And just to give a frame of reference to the temperatures that we're looking at here, at the hot end, we're looking at about 2,500 Kelvin all the way down to only a couple hundred Kelvin. So we're extending from, again, the low mass stars all the way down to overlapping with even some of the gas giants in our own solar system. But yeah, as a result of them not having hydrogen fusion in their cores, brown dwarfs will over time. And one really annoying result of this is that if you have just a single brown dwarf, and I should preface real quick for those who are not familiar with this, we're just looking at evolutionary tracks for everything from a low mass star all the way down to planets and how their temperatures evolve over time. And so if you find a brown dwarf just floating out in the galaxy all on its own, and it's at a specific temperature, without any other information, it's going to be nearly impossible to figure out whether you're looking at a really young giant exoplanet, a middle-aged, middle-mass brown dwarf, or an extremely old low-mass star. And this is the mass temperature age degeneracy, and it is annoyingly tricky on figuring out and characterizing the brown dwarf that you have now discovered. And not just that, but the cool temperatures within brown dwarf atmospheres give rise to a huge number of molecular species that cause all of these huge molecular absorption bands. What we're looking at here are spectral energy distributions for, at the very top, a like mid-M dwarf, all the way down to the bottom is Jupiter. And as we get down to colder and colder temperatures, you may notice that we're getting more and stronger molecular absorption features. And not just that, but we're actually losing that characteristic black body shape. And so even if you were able to get a high resolution spectrum of a brown dwarf, you still have a very hard time figuring out even basic things like metallicity. And so that can make it really, really tricky. And so if you have your brown dwarf just sitting out in the galaxy all on its lonesome, it's very mysterious. It does not want to give you any of its information. It doesn't want to talk to you. You can't figure anything out. On the other hand, main sequence stars, relatively, are very talkative. They want to tell you everything that you want to know. You can get their age, you can get their composition, you can get their metallicity. And so if you can determine that a star and a brown dwarf are moving together and are actually bound to one another, assuming that they form from the same natal environment, you can then apply the same properties of that main sequence star to the brown dwarf, breaking this degeneracy and now having a peek inside the hood, so to speak, of what's that brown dwarf is made of. And so we typically classify the benchmarks as having like three main properties that you can get out of them. First, on the left, we have our parallax benchmarks. So you can get parallaxes for many brown dwarfs now with Gaia DR3, but we are still very limited to the closest and the brightest ones. However, any brown dwarf that is co-moving with a main sequence star you can then apply the parallax of that star to the brown dwarf, allowing you to now do anything you want with a parallax. We can also get the age benchmarks. So if your brown dwarf is moving with anything that you can get an age from, maybe it's from a rotation rate, maybe it's from a white dwarf cooling time, maybe it's even moving with a bunch of other things in a young moving group, you can now apply that same age to the brown dwarf, again, breaking that mass, temperature, age degeneracy. And finally, we have the chemistry benchmarks. These are brown dwarfs that are co-moving with a solar type star, typically F, G, and K type stars. And with these, we have a much better handle on how to get elemental abundances and metallicity. And so if your brown dwarf is co-moving with one of these, you can now also, again, apply those same properties to the brown dwarf. So there have been a lot of benchmarks that have been discovered throughout the years, typically using the WISE survey, 2MASS, pan-stars, and many of these we do want to say are now available on the Simple Archive, where you can find information on the brown dwarf companions, their spectra, their photometry, as well as the association with their host star. But we're also discovering a lot of new benchmark systems through, for example, the Backyard Worlds Planet 9 Citizen Science Project. In this project, citizen scientists are looking at images from the WISE Space Telescope, as we're looking at here, flipped through different epochs of time. And many citizen scientists will notice that there seems to be a faint brown dwarf co-moving with some other bright star. And through this project, we have actually recently published a paper where we've discovered over 80 new benchmark systems. This is almost doubling the known population of benchmark systems. And I will say, if you want more information on all of these exciting systems, you can follow this link right here to our recent paper. And you're also going to hear about some more work today on even more brown dwarf benchmarks that are being discovered. So we're really entering a time where we're doubling and maybe going to triple the known benchmark population within the next year or two.
I'm going to try to take this. Okay. Just to finish up these slides here. So we have new benchmark systems. We also have these new modeling techniques that are sort of taking us into the future, retrieval modeling. And with this, we started to look at population statistics on these retrieved brown dwarfs. So these are not just benchmarks, these are also isolated systems, and we started to notice. So we have this age, mass, temperature degeneracy. We're also starting to see these sort of perhaps anomalous chemical signatures coming out, like super high C/O ratios. Among the retrieved brown dwarf population. And so the real motivation behind this Splinter is that these models don't really give us a lot of information without context, whether that's context from our solar system, from the solar neighborhood, or even within their own stellar systems. And so hopefully we have some of the leading experts in this room that are going to talk about what they can bring to the table. So we have in each session, we've sort of organized into 3 topics. We have insights from thermochemical behavior. This is predicted, it's also observed. We have a meteoriticist talking in our second session. We have new and or available benchmark data. So what data is available for us to use in our modeling, and that's on the substellar and the stellar side. And then we have these benchmark retrieval modeling studies that are being put into practice. What can we learn from them? So with that, I'm going to invite Shannon Vischer up to open our first session.